All right, let's dive into this explainer and explore how the differential transformer V2, or diff V2, elegantly solves some of the absolute biggest bottlenecks in modern large language models. If you've been following the AI space, you already know that the standard transformer architecture is the engine behind almost everything we build today. But it has flaws, specifically in how it processes attention. Today, we're looking at a fascinating piece of research from Microsoft proposing a drop-in replacement that might just fix those fundamental issues once and for all.
Here is our roadmap for today. We're going to start with the core problem with attention, meet diff V2, peek under the hood, see how they fix the math, and wrap up with some really exciting early results.
Okay, Section 1, the problem with attention. Why do we even need to fix the standard transformer?
So standard scaled dot product attention has literally powered the AI revolution. It's the core of models like GPT-4 and Llama. But what happens when its underlying math creates a ton of unnecessary noise? Researchers have realized that the standard attention mechanism actually forces the model to allocate attention, even when a specific token has absolutely nothing important to look at. Imagine forcing your brain to focus intently on a blank TV channel playing nothing but static. That's essentially what the model is doing.
The crucial point here is the softmax constraint. Standard softmax attention really struggles because its magnitude is strictly bounded. Since the attention weights mathematically have to sum to exactly 1, the context root mean square, or RMS, is trapped. It's strictly bounded between 1 over the square root of n and 1, so the model is forced to allocate that attention somewhere, even when it shouldn't. This creates what researchers call attention sinks, the core villain of our story today. These sinks are basically traps that force the model to focus on completely irrelevant tokens, like the first word in a sentence or some random punctuation, just to dump that mandatory attention weight. It's a huge waste.
Section 2, let's meet the differential transformer V2, the elegant drop-in solution.
Now, if you remember diff V1, it had had some brilliant ideas, but it came with major developer headaches. It suffered from slower decoding speeds, required custom developer kernels, and annoyingly loaded the value cache twice. Diff V2 totally strips those headaches away. It completely eliminates the need for custom kernels, its decoding speed matches the standard transformer perfectly, and you can just use standard flash attention right out of the box.
You might be wondering how it achieves those speeds. Well, LLM decoding is typically memory-bound rather than compute-bound, so keeping the key value cache size small is absolutely critical. By keeping the number of key value heads exactly the same as the baseline transformer, diff V2 beautifully avoids any memory-bound decoding delays. That means it achieves decoding speeds perfectly on par with the standard models we already rely on every day.
All right, Section 3. Let's look under the hood at this differential mechanism.
Here is the exact step-by-step breakdown of how diff V2 processes attention. First, it doubles the query heads compared to your baseline transformer. Second, it shares the key and value within the same grouped query attention, or GQA, group. And third, it subtracts the two resulting attention maps using a projected lambda scaling factor. If you want a real-world analogy, think of noise-canceling headphones. By generating two attention maps and subtracting them, we cancel out the static and isolate the true, pure signal. But there is a really crucial detail hidden right in the researcher's code. Those two subtraction heads absolutely must share the same key and value, meaning they have to be in the same GQA group. If you try subtracting heads that are not in the same group, the model goes haywire. You get severe training instability and massive loss spikes. Sharing that key and value is the mathematical anchor that actually makes the subtraction work.
Now, a lot of you are probably thinking, doesn't doubling the query heads make the model huge? Actually, no. By explicitly constructing this differential operation right before the output projection step, diff V2 actually saves a massive 25% of the attention module's output projection parameters. Where the standard transformer eats up its full parameter budget there, diff V2 shrinks it down. That means you get those saved parameters back to spend elsewhere in the model to make it even smarter.
Section 4. Fixing the math. Solving the magnification problem. 100x. When you're talking about the delicate mathematics of neural network training, 100x is a terrifying number. Back in diff V1, forcing the context RMS back to a value of 1 required a per-head RMS norm layer. At a standard sequence length of 8192 tokens, this normalization layer acted like a 100x magnifying glass. Imagine taking a tiny, microscopic error in your model and instantly blowing it up by a factor of 100. It was chaotic.
That 100x magnification caused massive gradient spikes and numerical instability when researchers tried to pre-train the model at scale. But here is the genius of diff V2. By fundamentally improving the parameterization, it completely removes that per-head RMS norm layer. It's almost funny how a beautifully simple deletion fixes such a catastrophic problem. But it elegantly restores training stability, keeping the gradients incredibly smooth and manageable, even deep into a massive training run.
This all builds to a complete mathematical fix. Remember that softmax constraint we talked about in the first section? Standard attention has a hard lower bound of 1 over the square root of n. Well, by using a token-specific, headwise projected lambda factor during the subtraction, diff-v2 shoves that lower bound all the way down to 0. By allowing the attention magnitude to literally hit 0, the model is no longer forced to pay attention. Those pesky attention sinks, they are finally eliminated for good.
Section 5. Early Results and Future. Let's look at some empirical observations at the 1 trillion token mark.
When put to the test on 1 trillion tokens, the empirical results are just incredibly strong. The researchers report a notably lower language modeling loss, a gap of 0.02 to 0.03, which is massive at this scale. They saw heavily reduced loss and gradient spikes, and amazingly, the model remained totally stable even under massive learning rates, like 64 to 1E3. Where a baseline transformer would easily crash and burn. It also drastically reduced the magnitude of activation outliers, making the whole model much easier to optimize. And it is vital to note that these are not just toy experiments run on tiny datasets. The researchers pushed this architecture through actual production-scale dense models and even a massive 30 billion parameter active mixture of experts, or MOE model. Proving it works in these grueling environments shows incredible robustness. It's truly ready for real-world application.
The community response has been fantastic too. This comment from user Programmer Solar on the Hugging Face blog perfectly captures the excitement. They pointed out that DFFDV2 isn't just some clever parameter-saving trick, but actually offers fundamental improvements in training dynamics and stability. I totally agree. It really is a fundamental leap forward in the mechanics of how these models learn to focus.
And that leaves us with a fascinating, provocative question to end on. If this elegant, noise-canceling math fixes the transformers so beautifully without needing any custom kernels, where else in AI architecture can we apply it next? Could differential attention be the key to unlocking the next generation of multimodal or state-space models? It's an incredibly exciting frontier that fundamentally changes how we think about attention. You should definitely check out the source paper, explore the code yourself, and imagine what you could build with it.